Hello students, today we will continue with the chapter on current electricity and the today's topic will be galvanometer and ammeter. We will be focusing on this two topics today and we'll continue with the discussion of what is a galvanometer. All of you would have seen a galvanometer in the lab with this apparatus. You have all of you have used this in the lab and also in the previous experiments that we have discussed previously, the potentiometer experiments, the Wheatstone meter bridge experiments, Kelvin's method using meter bridge. Everywhere we were using a galvanometer. With there we used to see the deflection, whether the deflection goes to the left or to the right, or it is showing zero deflection. These were the main points that we were doing with the galvanometer. But while using this galvanometer, we were not aware what was there inside of a galvanometer. See, here you have the indication with the pointer, so that you can see here also. This is the inner part of the galvanometer. What is there inside? There is a horseshoe magnet. At the four pole faces of a horseshoe magnet, you can see a coil that is fixed over a soft iron core, and this coil, this rectangular coil, gets deflected if there is any presence of current is there. And you can see, according to the presence of current or due to the presence of a potential difference, this coil gets deflected, and according to the deflection of the coil, the pointer will gets deflected accordingly on the scale which we observe here. But here you can see, here the pointer is connected to the rectangular coil. Now when you are using the galvanometer, it is able to detect the presence of very slight current as well as a very slight potential difference can be detected with the help of a galvanometer. And therefore we can use this galvanometer as a voltmeter or as an ammeter. So with the suitable changes made, we can convert a galvanometer into an ammeter or a voltmeter. So today's session we will see how this galvanometer can be converted into an ammeter. So we will move to the next slide. Here galvanometer, how we will see how this galvanometer is converted into an ammeter. Now before converting this galvanometer into an ammeter, the current capacity of the galvanometer has to be increased. That means basically when we see a galvanometer, it has a current carrying capacity. But when we have to use it as a current measuring instrument, that is an ammeter. Ammeter is a current measuring instrument. So when we are converting a galvanometer into an ammeter, it is mostly measuring the current, and therefore we have to increase the current carrying capacity to convert a galvanometer into an ammeter. And you know, ammeter, when we are measuring, when we are using it to measure the current, how do we connect it in the circuit? It is normally connected in series with the circuit. So if you are connecting it series with the circuit, the resistance of the ammeter has to be minimum, or it should have very minimum resistance for the galvanometer. Or in an ideal case, an ideal ammeter should have zero resistance. So what we have to do is, the resistance of the galvanometer has to be so adjusted that its resistance is minimum, so that it will be converted into an ammeter. Now if a very high current is passing through this ammeter, there are chances that the needle may get bent, and that may damage the instrument that we are using to measure the current. So in order to, we have to protect the instrument from all these possible problems. So all these problems can be solved, or these points can be achieved, that is increasing the capacity of the current capacity, and effective resistance of the galvanometer is decreased, and then protecting this instrument from all the damages. All this can be achieved by connecting a very low resistance in parallel to the galvanometer, which is called as the shunt resistance. Now when you connect a very low resistance in parallel to the galvanometer, that will give an alternate pathway for the current, and therefore offering minimum resistance to the flow of current. That is why we are connecting the shunt in parallel to the galvanometer. Then this galvanometer, in the next slide we will see, when the galvanometer connected in parallel to a shunt resistance will act as an ammeter. So we will see in the next slide how this galvanometer is converted into an ammeter by connecting the shunt resistance, and what are the uses of this shunt. Now as we have already said that by connecting a shunt resistance parallel to the galvanometer, it will be protecting the instrument from further damage causing to the needle by the flow of high current through the ammeter, and you can increase the range of the ammeter. That means the current carrying capacity is increased. Suppose initially the galvanometer was able to measure only some 1 milliampere or 1 microampere current, microampere is detected. Then when we are converting that into an ammeter, if we want to increase the range, accordingly we can connect a shunt resistance which will increase the range of the ammeter. So the shunt will help in increasing the range. Then the effective resistance between the points where we are connecting the ammeter can be decreased by connecting the shunt resistance. So all these 3 points will be obtained with the help of shunt. Now we will see how the shunt resistance calculations are done, or we want to find out what shunt has to be connected so that the galvanometer range can be increased to a particular value, or it has to be protected from damages, and this can be understood in the following discussions. Now here, as you have said, as I have already mentioned, that the shunt resistance is connected parallel to the galvanometer. So you can see S and G are parallel. Two resistances are connected parallel to each other. Galvanometer has a resistance which is represented by capital G, and the shunt resistance is represented by S. Now you can see two resistances connected parallel. So the potential drop across the galvanometer must be equal to the potential drop across the shunt resistance. So what you will get, the expression is Ig into G will be equal to Is into S. So Ig into G represents the potential fall across the galvanometer resistance, and Is into S will be the potential drop across the shunt resistance. Now you know, according to the Kirchhoff's first law, you know the current I that is coming through the resistor is reaching the junction here, and it is branching out into Ig and Is, which means that I must be equal to Ig plus Is. So you can write Is as I minus Ig, because I is equal to Ig plus Is. So substituting that in this expression, you can calculate the value of S if we know the value of Ig and I. What is this I? I is the current that we are supposed to measure using the ammeter, and Ig is the current which will give a full scale deflection by the galvanometer. Galvanometer will give a full scale deflection for a current of Ig, and I is the current that we want to measure. So in order to measure a current I, you have to connect a shunt resistance parallel to the galvanometer according to this calculation, where we know the galvanometer resistance is capital G. Now you have got the calculation of the shunt resistance is equal to G into Ig divided by I minus Ig. Now suppose we want to increase the current measuring capacity to N times Ig. That is Ig. Now you can see here this rectangular box within this. Now this is called an ammeter. Now initially we had simply this much part. When we connect this shunt resistance to this galvanometer parallel, this becomes an ammeter. So here if we want to increase the current capacity to I, that is N times Ig, we will try to find out what is the value of N. Should be here. You can see the shunt resistance S will be equal to G into Ig. In the place of I, we are substituting N times Ig. That is the maximum current that we have to measure using this ammeter will be equal to Nig, or the shunt that has to be connected will be equal to G into Ig divided by N into Ig minus Ig. You can see Ig can be taken outside, common factor can be cancelled, and final expression for the shunt you will get S is equal to G divided by N minus 1. So by the understanding of basically these 2 points, you will be able to solve the problems based on these calculations using the ammeter. Now this you can see the value of S that we have got here will be the shunt required to increase the range of the ammeter by N times the value of H. Now we will try to find out what is the current that is flowing through the shunt, that is represented by Is. Is represents the current through the shunt. Now how we will do the calculation? You know that I is equal to Ig plus Is. So in the place of Is we can write it as I minus Ig, or in the place of Ig we can write it as I minus Is. So Is is the current through the shunt, and you will get this expression Ig into G is equal to Is into S. That is the basic thing. That is the potential fall across G must be equal to the potential fall across S. So substituting in the place of Ig as I minus Is, here we are trying to find out the value of S. So both the terms here unknown is Is. So we are both sides we have only Is term. So we can find out the value of Is by solving the equation, and we will get Is into G plus S is equal to G into I. Now next step, we will get the fraction of the current flowing through the shunt as the ratio Is divided by I is equal to G divided by G plus S. This is the shunt resist. This is the fraction of the current flowing through the shunt. Or if you want to simply calculate Is, you can multiply the right hand side with the value of I. So you will get the shunt current through the shunt resistance. Now we will try to solve a problem based on what we have understood till now. So we have the problem stating that a galvanometer has a resistance of 100 ohm and its full scale deflection current is 100 microamperes. What shunt resistance should be added so that the ammeter can have a range of 0 to 10 milliampere? So we will first try to understand the problem. The galvanometer has a resistance of 100 ohm, means G is equal to 100 ohm, and its full scale deflection current is 100 microampere, which means that Ig is the current that flows through the galvanometer to give it a full scale deflection, that is 100 microampere. Now we want to change this galvanometer into an ammeter which reads maximum of 10 milliampere. So we have to increase the range from 0 to 10 milliampere range. That is, initially it was reading only 100 microampere. Now we want to read a current of 10 milliampere. So we want to find out the shunt. That is the question. So we know that Ig is equal to 100 microampere converted into ampere. You will get it is 100 into 10 to the power minus 6 amperes, and the maximum current that we want to measure is 10 milliampere, which is equal to 10 into 10 to the power minus 3 amperes, that is converting milliampere into amperes, multiplying by 10 to the power minus 3. Now we know the expression. Now I is equal to n times Ig. So we will try to get the value of n here. How many times the current carrying capacity is increased. So you will get, by dividing this, you will get n is equal to 100. Now after getting n is equal to 100, we know the value of capital G, and we know the expression S is equal to G divided by n minus 1. So from this you will get the equation S is equal to 100 divided by 99. That will be the value of the shunt resistance to be connected parallel to the galvanometer, so that it will be converted into an ammeter which will be reading 0 to 10 milliamperes. In the next slide, again, we try to solve another problem. So in this problem, what is the problem reading? What is the resistance value of the shunt resistance that will allow 20% of the main current through the galvanometer of 99 ohms? Means the galvanometer resistance G is equal to 99 ohms and Ig is equal to 20%. That means 20% only current should pass through the galvanometer. This shunt will allow the current of 80% should pass through the shunt. So we have to select the shunt in such a way that 80% is passing through the shunt and only 20% is allowed to pass through the galvanometer, so that the needle is not damaged. Like in the beginning we have seen that when we are connecting a shunt resistance, we normally select the shunt resistance. Why we are connecting the shunt resistance? In order to protect the instrument from damage. So most of the current should pass through the shunt. Shunt is providing an easy way path for the main current to flow through, and that way the current carrying capacity is increased. So we will try to solve this. You know that Ig is only 20% of I. So which means that 80% is passing through the shunt. So you can write 80% of I, which is equal to 0.8 times I. And you know the calculation, 20% of I will be 0.2 times I. And in the next step, we apply the condition Ig into G will be equal to Is into S. Because we know the value of G, we are supposed to find out the value of S. We know the value of Ig and Is. So we can use this formula to calculate the shunt resistance value. After doing the calculation, you get it to be equal to 247.5 ohms. So with that, we end today's session, and we will discuss the further things in the next slide. Thank you so much, and drop your doubts in the comments section.